In this session, we will be discussing about the different configurations of parallel manipulator. So as we have seen in the earlier session, a parallel manipulator, it has a closed loop kinematic chain, and it is made up of a mobile platform that we call it as the end effector, or it is the moving platform with n degrees of freedom, and it has a fixed base which is linked by, say, m independent kinematic chains. So these kinematic chains are the assemblages of the links and joints, and the actuation takes place through k simple actuators in the chosen joints. So let us remember the variables k, m, and n. So k here is the number of actuators, and M refers to the kinematic chains or legs. We can say the M refers to the independent kinematic chains or legs, and N refers to the degrees of freedom. So you can have different configurations by depending upon these three variables. So let us see how it is. So according to the definition, if K is equal to N, so what is K? K is nothing but the number of actuators, and N is the degrees of freedom, and we also have one more variable, that is M. M refers to the number of independent kinematic chains or legs, right? So if we have K is equal to N, which means the number of actuators and the degrees of freedom are equal, then we call the configuration, we call it as non-redundantly driven parallel mechanism, right? And if the number of actuators is greater than the degrees of freedom, then we call it as redundantly driven parallel mechanism, right? So then the third configuration is if M is greater than N. So that is if the number of independent kinematic chains are greater than the degrees of freedom, then the parallel mechanism is having a configuration with redundant legs, right? And whereas if it is M less than N, then the parallel mechanism with one or more actuated joints in each leg will be referred to as hybrid parallel mechanism, right? If all the three, that is M equal to M equal to K, then we call it as a fully parallel mechanism. So these are the different configurations of a parallel manipulator. So a parallel manipulator, it can be either non-redundantly driven parallel mechanism or redundantly driven parallel mechanism, right? Or it can have it is a parallel mechanism with redundant legs, right? Or it can be a hybrid parallel mechanism or fully parallel mechanism. So depending upon the variables, that is the number of actuators, number of degrees of freedom, and number of legs that you have in the parallel mechanism, you can just have different configurations of the manipulator. So here, fully parallel robots, that is, they are the robots which has equal number of chains and equal number of that is the number of chains or equal to the degrees of freedom of the end effector. So that we call it as fully parallel manipulator. So that can be either planar type, a fully parallel mechanism. It can be either planar or spatial, right? So fully parallel planar, so as you see in this figure, this is an example for fully parallel planar, and it has the moving platform with 3 degree of freedom. So the moving platform or the end effector will be having 3 degrees of freedom that will be constrained to perform 2 translations and 1 rotations. 2 translation and 1 rotations. So 3 chains support the end effector, as you see in the figure. 3 chains will be supporting the end effector, and the chains are attached at 3 points. So the chains are attached at 3 points. Generally, the end effector will be a triangle. So the end effector will be a triangle. So like this, you will have the end effector will be a triangle, and at these 3 points, you will have three kinematic chains, right? So we'll be having three kinematic chains. So again, it will be having a fixed base also, right? So three kinematic chains it will be having. So the end effector here it will be a triangle. So mobility will be zero when the actuators are locked. So this is a fully parallel manipulator which is planar, right? Then you also have cable driven. So you also have the cable driven parallel manipulators as you see in this figure. So these manipulators they have flexible cables. So the as you see here in this figure, they are the flexible cables. So they are the flexible cables, and they are used to take uh, I mean they are the part of the rigid links, right? So as you have rigid links in the manipulator, so the cables here they take the place of a rigid link. So the advantage of these cable driven manipulators are they include more workspace, right? So they will have more greater workspace, and also payload high payload to weight ratio, right? And low manufacturing cost, right? So these are the advantages of cable driven manipulators. So the first advantage is that they have greater workspace, and they have high payload to weight ratio and low manufacturing cost, right? So the cable driven parallel manipulators, say with the n degrees of freedom, which are driven by M cables, they can be further classified into three types. So cable driven manipulators can be further classified into three types. So let me write it as cable driven parallel manipulators. They can be classified into three types depending upon the number of cables that you have used. Let us say if you are using M cables, and the uh, and if it is having n degrees of freedom. So M cables and n degrees of freedom, right? So based on that, you can further classify the cable driven parallel manipulators to under constraint, under constraint, then full constraint, and redundantly constrained, right? Redundantly constrained. So if it is under constraint, which means the condition is that n plus 1 should be greater than m, right? So if the position and orientation are determined by gravity. So in this case, for under constraint, the cable driven parallel manipulators, the position and orientation are determined by gravity. So it is under constraint if at all n plus 1, where n refers to the degrees of freedom and m is the number of cables used, right? So n plus 1 is greater than m is the condition for it being an under constrained parallel manipulator, cable driven parallel manipulator, and the condition for it being a fully constrained cable driven parallel manipulator is that n plus 1 should be equal to m. So obviously you can just tell that a redundantly constrained parallel manipulator, the condition will be n plus 1 less than m. So you have the fully constrained and the redundantly constrained cable driven parallel manipulators, where you determine the position and orientation by the length of the cable. So in the first case, that is the under constraint, the cable driven parallel manipulators, we determine the position and orientation by gravity, whereas for the fully constrained and the redundantly constrained cable driven parallel manipulators, we determine the position and orientation by the length of the cables, right? Next, we also have the parallel mechanism to be either symmetric or asymmetric. So there are certain conditions for a parallel mechanism to be symmetrical. So the first condition is that it has to be a fully parallel mechanism. So what is the condition for a fully parallel mechanism? That is, the number of actuators should be equal to the number of degree of freedom that should be equal to the independent kinematic chains, right? So this is the condition for it to be a fully parallel mechanism. So for we can say the parallel mechanism is symmetrical if it is a fully parallel mechanism. And the second thing is that the arrangement of joints that has been attached to the mobile platform, that is the end effector, and the fixed base, it should comply with certain specified rules, right? And the third point is that the corresponding fixed length links that you have in the legs or the kinematic independent kinematic chains should have the same length. So all the fixed length links should have the same length. And the type of the joint and the number of joints that you use in the legs should also be arranged in identical pattern, right? So the number and the location of the actuated joints in all the legs are the same. So as you know that in a parallel mechanism, you can also have passive joints that are not actuated. But however, you say the parallel mechanism is symmetric only if the number and the location of the actuated joints in all the legs are same. So these are the conditions that has to be satisfied for a parallel mechanism to be symmetric. So once again, I just repeat. So the first condition is that it has to be a fully parallel mechanism, and the joint arrangement that is which connects the end effector and the base has to comply with certain specified rules, and the corresponding fixed length links should have the same length, and also the type of the joint and the number of the joints that are used in all the legs should be arranged in an identical pattern, and the number and location of the actuated joints in all the legs are the same. So if this conditions are satisfied, then we say the parallel mechanism is symmetric.